All right, yes, thanks a lot. I'm very grateful for the opportunity to speak here, and I think it's a really great thing that you're doing with the seminars, so I'm very happy about this. So yeah, today I'm going to be talking about this three recent work with Sasha Grazdano about thermal field theory correlators in the large N limit and some new interesting results that we've gotten here. Okay. So the talk is going to consist mainly of two parts. One is going to be broader, more general, where I'm going to talk about the analytic structure of retarded correlators in large and thermal theories. And I'm going to talk about thermal spectra, quasi-normal modes, double trace deformations, things like that, and then describe some interesting new results and analytic properties. And then I'm going to turn to 3D conformal theories, where it turns out that sort of things become a lot more powerful. So I'm going to start off with the familiar particle-vortex duality, and then I'm going to be talking about a very interesting set of dualities of conserved currents in 3D conformal field theories, and try to paint a sort of a general picture that seems to emerge from that. So let's start with this first part. So the setup that I'm going to be thinking about throughout is large N holographic CFT. So by large N, I mean it's a large matrix N, so the local Hilbert space is infinite dimensional, and I'm always going to be thinking about the thermal state. Now, entirety of this talk is inspired by holographic studies, and it's very difficult to present any real results for non-holographic systems. But, say conjecturally, a lot of what I'm going to be talking about here may hold outside the holographic domain, and I'm going to mostly focus my talk on really the QFT language without very explicit references to the holographic dual. So that should be kept in mind. So we have a thermal CFT, and suppose we have some Hermitian local single trace operator. By single trace we mean scales linearly with n, and it has some scaling dimension, delta. And this operator is sourced in the action by some external source. And the central object will be, so I'm really thinking about the real-time theory, and the central object here is going to be the retarded correlator. So the retarded correlator, so do you see my cursor waving around? Okay, so the retarded correlator is essentially just the commutator of the operator with itself at different times, which I'm going to call the spectral function, and the retarded correlator is sort of the causal incarnation, the causal incarnation of that, multiplied by the Heaviside function, and it encodes the causal response of a system to an external perturbation. So this is really going to be the central object of my focus, and I will consider it in Fourier space as a function of the complex frequency. And I'm gonna suppress the spatial dependence throughout, so it's all gonna be happening at some fixed momentum, some fixed wave vector. And the spectral function is essentially just the analytically extended imaginary part of the retarded correlator. So this should all be familiar. So to go through some properties that I'm gonna use throughout the talk. So there are the sort of generic textbook properties that are just universal in any QFT for any retarded correlator. So first of all, retarded correlators are analytic in the upper complex half plane. That's a consequence of stability and causality, and there are some other properties about complex conjugation and positivity that arise from unitarity and hermeticity and things like that. Now, where it gets more interesting is that I'm going to assume sort of power law asymptotics on these correlators. So what I mean by that is, First of all, the correlators should have sensible real-time Fourier transformation, so they shouldn't behave too wildly in the complex plane. And there are arguments that one can get from OPE and also from concrete holographic examples that these two assumptions that I've written down should hold in some sense. So they're sort of cartoonish, they're cartoonish incarnations of some more technically precise assumptions that I'm not gonna write down here explicitly, but in essence they boil down to the fact that we expect the retarded correlator to behave with some power law in all the directions of the complex plane that don't cross any singularities. And we expect that the spectral function doesn't have to scale as a power law in complex infinity, but it has to be bounded by some power law. And again, these are not proven from QFT. These are not they're sort of reasonable assumptions that one sees in real examples, and it turns out that they work and that they're sensible assumptions to make. Now, the critical assumption is that in large n limit, the only singularities of the retarded correlator are expected to be poles, so we don't expect any branch cuts. Now, this has a very clear incarnation in holographic theories, where the spectrum just consists of quasi-normal modes and not of branch cuts. Of course, there is no proof of that for a general large n QFT, but there was, within this thermal seminar series, a very interesting talk by Matthew Doddelson, where he constructed a model that doesn't have a known holographic dual, but is a meromorphic function of frequency. So meromorphic means that it's just there are just poles and no branch cuts. And these poles, the set of these poles, which are all in the lower complex half-plane, are the spectrum of the correlator. And that's something that I will assume throughout the talk. And the final, perhaps the most contentful assumption is the thermal product hypothesis, which was put forward in this beautiful work by the CERN group 2 years ago. And it's essentially a statement about the spectral function. So the statement is essentially that this combination here is an entire function of order 1, which means that it grows at most exponentially. And in practice, what this means is that the spectral function, which is just the commutator, has only zeros at the multiples of the Matsubara frequencies, so at the zeros of this sinh, and one can use that fact to really just write the spectral function down as a product over all poles, and that determines it almost uniquely. The only thing that's left is a constant, which can be dependent on momentum and temperature and things like that, but not the frequency. Spectral function is almost completely determined by the spectrum, and this is something that I'm going to be assuming throughout the talk. Is that all good? Are there any questions so far? All right, please feel free to interrupt me and stop me with questions. All right, so the retarded correlators are interesting because they encode the physical causal response that one can actually measure in a lab. But they're also interesting if we consider the double trace deformations of a theory. And so we take our action of our CFT, and we have some retarded correlator as defined here with some operator, and then we square this operator and deform that QFT with the square of this operator. It's called in this context a double trace deformation. And in the large n limit, it is simple, even in a thermal state, to compute what the retarded correlator is in this deformed theory. And it turns out that the object that is interesting here is the retarded correlator. And what happens is that if I denote by GF the new deformed retarded correlator, the poles of this new retarded correlator, so the spectrum, coincides with the zeros of the non-deformed correlator plus some constant that depends on coupling. So in other words, we can define this function here, which is the original retarded correlator plus some constants, and the zeros of this function are going to be the poles of the new retarded correlator. And that's interesting for several reasons. First of all, so this double trace story is 20 years old, but perhaps what is not often emphasized in literature is the fact that the spectrum of all the double trace deformed theories is encoded in the retarded correlator. It's not encoded in the spectral function, it's not recorded in the two-sided Whiteman, it's really recorded in the retarded correlator, and it's in fact the zeros of this correlator that gives you the spectrum of the deformed theory. And so adding a constant here doesn't change any of the assumptions that I was naming before, so we're just free to do that. It's essentially just a contact term. So that essentially makes the question of what is the behavior of zeros of a retarded correlator a relevant question, because the zeros of a retarded correlator are just the spectrum of some deformed theory. So in the big picture, we can start at some CFT, and if the scaling dimension is appropriate, we can trigger a relevant deformation. And if we take this coupling to infinity, we're going to hit another CFT in the deep IR, where we're going to have some other operator, where the original operator is going to be deformed into another operator with a different scaling dimension. And there we really have the two correlators in two theories, the UV theory and the IR theory, and the poles of one are the zeros of another. And one way to see it is this essentially amounts to a Legendre transform, and it amounts to an equation like this that you see below, and we're going to be seeing a lot of equations like this today. And holographically, the story is just a swap between Dirichlet boundary conditions and Neumann boundary conditions and the corresponding quasi-normal modes that one computes from the bulk wave equation.
Sorry, can I ask something?
Please.
Just a remark. So, does this deformation can this deformation be also irrelevant, like in the large n limit of Gross-Neveu models, etc.? Like, if you have a psi bar psi operator in a three-dimensional Gross-Neveu model, this has dimension 2, and psi bar psi square has dimension 4, so it's irrelevant. So you flow to the UV rather than to IR. And have you seen this picture?
Yeah, so I don't think there should be any problem with that. So the only thing really in my discussion today that could happen is that if your deformation is not going to be physical, or it's not going to lead to a stable theory or something like that, your spectrum is going to become unstable. It's going to escape to the upper half plane. But other than that, everything I'm going to discuss is completely robust. We can do an irrelevant deformation, and we can compute a correlator in the IR and do an irrelevant deformation, and the zeros of the original correlator are going to be the poles of the deformed theory.
So in this remark, you can actually add a double trace higher spin deformation.
I'm gonna turn to this. I'm gonna turn to this.
Okay.
Yes, later on.
Good, thank you.
Okay, so now that I justified why we should be interested in zeros of the retarded correlator, I can present this nice result that happens when we put all of these pieces of the puzzle together. So if we have the spectrum of zeros denoted by omega n minus, so first of all the assumptions that I wrote down, one can derive a number of constraints and identities involving poles and zeros. One can write different sum rules. One can make precise statements about how these poles and zeros should be distributed in the complex plane. So I won't go through all of that today. So if one assumes the standard holographic Christmas tree configurations, one can also derive all sorts of constraints. Again, I'm not going to focus on this today. What I will tell you about, though, is this thing that we call spectral duality relation. So the retarded correlator, we can write it down as a product over zeros and poles like this. And this is interesting because this is not a fraction of convergent products, because one would usually need some Weierstrass or Hadamard theorems for that. But because the retarded correlator has this special power law asymptotic properties, one can generically just write it down as this trivial product over poles and zeros. And because poles and zeros are both gonna lie because of stability reasons in the lower complex half plane, one can define this function, which we call S, which has zeros where the poles are in the lower half plane, and it has zeros in the upper half plane on the mirrored positions of the zeros of the retarded correlator. So it's essentially a function which encodes all the same spectral data as the retarded correlator. And if we now use the thermal product formula, one can show that these two spectra, which can be understood as a spectra of some double trace deformed theories, obey this identity, the spectral duality relation. So the odd part of this function is essentially fixed to be a sinh. Now, how should one understand this? Well, first of all, this is essentially an identity for every choice of omega. So it's an infinite number of identities. And one has this lambda factor here, which can depend on momentum or coupling or temperature, but it doesn't depend on the frequency. And one should understand this as, so if we have this RG flow here, and we take the coupling from 0 to infinity, we can pick any 2 points on this flow, and we're going to have two different spectra at these 2 points, and the spectra at these 2 points are going to obey this spectral duality relation. And it turns out that essentially this is enough to derive one spectrum from the other alone. So yeah, as I said, it relates the spectra between different double trace couplings, holds between any 2 values of couplings, and should be understood as an infinite number of constraints between these 2 spectra. Any questions? All right. So we can verify this with a very simple example of a CFT2 dual to a BTZ black hole. This is an example that we can just solve. Please. Mm-hmm. 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 Not sure I understand what you mean. So, yeah. Mm-hmm. 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 But So you say you get a sum of you get a sum of some exponentially suppressed terms, but that doesn't tell you what the correlator behaves like at large omega, does it? Or yeah, so there is one way to see this, to see why G has to obey a power law at large omega in all the directions of the complex plane, or at least intuitively sort of expected, is that 1 over G also has to be a sensible correlator upon this double trace deformation, and it pretty much tells you that it has to be a power law. That's sort of a hand-wavy intuition. But yeah, I would be very interested about the rigorous statements one can make through OPE in the complex plane. But that's maybe for. No, for every. Yeah. All right.
Can I say also just a question? Does it have any meaning that the sines of beta omega 2 is like the partition function of a harmonic oscillator?
I mean, this just at the end of the day comes from the thermal circle somehow. It's.
Is there any deeper meaning to that? Like for any CFTs, you get 1 over the partition function of one single harmonic oscillator somehow for a given omega?
I don't know how to answer that well. It's the same singe that's in the Whiteman correlators. It's the same thing that's in the fluctuation dissipation. It's sort of appears everywhere. So gravitationally, it appears from horizon properties. You can see it with the Frobenius expansion around the horizon and things like that. But I don't have a good answer for a deeper meaning here. It would be very interesting to understand that better.
Okay, thank you.
Okay, so right, we have this explicit example of a CFT2 dual to a BTZ and some scalar primary operators, which we parameterize as 1 minus nu in the UV, and that's going to flow to an operator with scaling dimension of 1 plus nu in the IR. And the spectra are very simple. They're just equidistant points aligned vertically in the complex plane. And one can write down the retarded correlator explicitly. That's been known for 20 years. And this function S that I have defined here, one can also just evaluate explicitly, and one can evaluate that the spectral duality relation holds, so the odd part of this S is indeed proportional to the singe. And this S contains all the spectral information. Now, the study of spectra and the double trace deformation is nothing that's of course new to our work, but if one plays around with this, one actually gets to see some interesting behaviors of the spectra and the double trace deformation. So I decided to show you what goes on here. So we have this very simple example of a BTZ of a CFT2 dual to a BTZ black hole, and we have the thermal spectrum, and we interpolate between the IR and the UV CFTs. Now we work at some finite momentum, and we have this nu that is essentially parametrizing the difference between the scaling dimensions in the UV and in the IR. And so as you see, for these choices of nu, nothing particularly wild is going on. It is kind of interesting that these trajectories in the complex plane, as we change the coupling, are sort of curved. But as we change this parameter that parameterizes the scaling dimension, the interesting things start going on. And I'm showing this to you because I find it so interesting that something as thoroughly boring as the BTZ spectrum actually exhibits interesting behavior under double trace deformations. So maybe somebody has done this before. I don't know I haven't seen these plots before. So we can see that essentially as we change this parameter that determines the scaling dimensions, one of the poles escapes to infinity, and some of the poles start moving up as we go to the UV, and some start moving down as we go to the UV. And what's interesting is that as we turn in the UV the relevant deformation, what is immediately most affected is the IR part of the spectrum, so the part of the spectrum that's close to the complex origin, and then the UV part follows. And if we go from the IR to the UV with an irrelevant deformation, then the opposite happens. We first get this sort of wave that starts at the deep UV and then travels towards the IR. And then we can sort of increase, even go further, and we see that the choice of the pair of poles that escapes to infinity changes as we change its dimension. So I thought that was interesting, and what's also interesting is that one can actually understand some things from this plot alone. So the distance, the asymptotic distance between these endpoints in the UV and the IR is related to this scaling dimension parameter and is related to the asymptotic behavior of the retarded correlators. So one can read all sorts of things from this, and one can also go to more interesting numerical examples. So here, before I go to numerical examples, here you can see for all sorts of scaling dimensions what happens between the UV and the IR. You see these little islands here, these sort of level crossing things that go on. So I have nothing particularly physical to say about this. I just thought it was very interesting to encounter such subtle behavior in an example that is as simple as the BTZ. Any questions about this? All right, so now we can do the same calculation for say scalar primaries in the n equals 4 super Young Mills. So these are just minimally coupled scalars on the background of Schwarzschild black hole, and here we can use this spectral duality relation that I told you about before to essentially, we can just compute the spectrum at the UV fixed point, and that is completely sufficient to derive all the other double trace deformed spectra. So we don't actually have to compute we don't actually have to solve the bulk wave equation with all sorts of boundary conditions, which correspond to different points in between the fixed points, but we can just compute the UV spectrum, and then the spectral duality relation in this thermal product formula stuff essentially just completely fixes the rest. And any 2 points between the UV and the IR here, any 2 points obey this spectral duality relation, and we can play with the scaling dimension here as well. So here we have this nu to be 1/3. We can increase the nu to be 2/3. Now with super Young Mills, we didn't see the interesting behavior as we did for the BTZ, but then again, we just tried 2 different scaling dimensions, so maybe there are things hidden behind it. And so interestingly, there is a lot, again, that one can read from this plot. For example, this distance here, it's essentially proportional to this scaling dimension parameter. So here it was 1/3, it was smaller. Here it's 2/3, it's twice as big. And there are also all sorts of things that just arise from the assumptions about power law asymptotics. One is that you will notice that at the UV fixed point and at the IR fixed point, this Christmas tree asymptotics is essentially the same. So this line doesn't change direction and it doesn't change the spacing. The only thing that changes between the fixed points is the offset. And that turns out is generic, and that's implied by the power law asymptotics of the retarded correlator. So what cannot happen is that this asymptotic angle would change direction, because that would violate the asymptotic power law. So that's all sorts of interesting things that one can see from that. All right. Are there any questions about this part?
Sorry, just to be sure and understand. So here what you do is to solve the wave equation 1 point, essentially, let's say in the UV, and then what you do is you use this relation to compute at all the other points, the quasi-normal modes, essentially, right?
Yes.
Okay, and what is in the what is happening in the dual, essentially? Because in the CFTs, this deformation, and in the bulk is what is like
you're interpolating
boundary condition.
Yeah, you're interpolating between Neumann and Dirichlet boundary conditions.
I see.
But you don't have to explicitly do that. You can you can verify this in a number of ways, but the point is that you really have to do the numerics once. Again, this is sort of a sanity check. I think I'm gonna get to the more interesting part now, but I think it's still interesting to see this this sort of worms on these RG plots here, these squiggles. It's kind of fun.
I see. Okay, thank you.
Yeah. I have no idea. So there are two options. Maybe it's not there, or maybe I just would have to try more scaling dimensions. So for BTZ, the solutions are explicit, so it's very easy to just do whatever you like. Here, for every scaling dimension, one has to really compute about 50 or 60 quasi-normal modes numerically to really do reliable numerics with that. So it's quite a time-consuming thing. So maybe if we would do a more thorough examination, it would pop up. But yeah, I don't know.
But did you observe for the BTZ some dimensions for which the escaping mechanism was not happening?
No. So the pair of poles that escapes to infinity just goes deeper and deeper towards infinity, but it's always there. You just have to go far enough. Also, there is also an interesting thing here. One can understand this as a dynamical system where the coupling is time, and the poles, the quasi-normal modes, are your variables, and you can express how a quasi-normal mode shifts when you change the coupling for just a bit, and you express that with all the other quasi-normal modes, so you get essentially a dynamical system. And it turns out that the direction in which the quasi-normal mode moves is precisely proportional to the residue of that pole. So there are all sorts of fun structures one can play with here. All right. So now I'm gonna move to CFT3s, which is more interesting, but has less pretty pictures. Actually, it has no pretty pictures, and I'm going to start with a known story of particle-vortex duality, and then I'm going to extrapolate from that into a more interesting set of dualities that hasn't really been thoroughly investigated until now. So let's consider a CFT3 with a conserved U1 current. So we have a conserved U1 current, and we can source it by putting this CFT in an external U1 gauge field. That so we can do variational derivatives with respect to the gauge field, and we get the expectation value of the conserved current. And because we're in a thermal state, this is not Lorentz invariant, and the retarded correlators of the conserved current splits into two channels. So actually, in if we break parity invariance, it splits into 3 channels, but let's assume we don't have any breaking of parity invariance, so it splits into 2 channels. The longitudinal channel of fluctuations parallel to the momentum, and the transfers with the fluctuations perpendicular to the momentum. So the longitudinal channel is known for the charge diffusion mode, and the transverse channel doesn't have a hydrodynamic mode at all. And yeah, one can, in the same way, compute this from, say, holographic theories. And where the story of what I was telling you before comes into play is we consider particle-vortex duality. So we have some CFT, call it CFT-A, with some conserved U1 current, and the dynamics of the conserved current are described by the retarded correlators G plus minus A. And particle-vortex dual of that theory is essentially we promote this external gauge field into a dynamical field, and then, because we're in 3 dimensions, we get a new conserved current, which is essentially a topological conserved current, which is fulfilled trivially through Bianchi identities. But we can still, because A is dynamical, we can compute the new correlators in CFTB. And we get equations like this that relate the longitudinal and transverse channels between the 2 theories. And as you see, this is exactly what we've seen before. So we can use spectral reality relation to relate those spectra between the theory A and theory B. So I can know the spectra in theory A, I can compute the spectra from theory B, the particle-vortex dual, through essentially the methods I described to you before. All right. So also to the question that Anastasia asked before, we can deform between these 2 theories continuously with essentially Maxwell deformations, which are in one sense higher spin generalizations of the double trace deformation. So we can play the same game here. And okay. What's especially interesting is if we have a self-duality. That means that the 2-point functions between the 2 theories are the same. And then we just have this one simple relation between G plus and G minus within the same theory. So we can compute the transverse spectrum from the longitudinal one, or vice versa, within the same theory. And that happens, as was noted almost 20 years ago by Herzog-Koft and Sajdev and Son in this holographic context. This happens due to electric magnetic self-duality of the Maxwell bulk in such theories. So a class of such theories that exhibit this self-duality are holographic theories dual to a Maxwell dynamics, and there we have Maxwell dynamics is invariant with respect to the swap of electric and magnetic fields, and this results in this self-duality structure, which allows us to compute the transverse spectrum from the longitudinal and vice versa. And this gives you all sorts of things. So, for example, this S function at 0 momentum reduces to a simple sinh, which means that all the poles converge to Matsubara frequencies. And this is sort of known. Sajdev had a couple of papers about this. But it's interesting to see from this new perspective. One can compute conductivity from that and things like that. So this is essentially a known story. The key point I wanted to make here is that there is a self-duality structure that can map spectra within the same theory. All right. So now I'm gonna talk about gravity for a bit. So we consider theories dual to ADS4 black holes in Einstein-Maxwell, and if we have some static black hole, we can perturb it. We have some background electric field, we have some background metric, and it turns out that in 4D specifically there exists a duality map between the solutions of the longitudinal just a second. All right, so in 4D specifically, the analysis splits into this longitudinal channel and the transverse channel. But there exist these maps that map from one channel to another, and sorry, there exists this maps that map from one channel to another, and they're controlled by this algebraically special frequency in the following sense. So we can solve the equations of motion for longitudinal waves, and we can just derive the solution to the transverse wave equation from that, as long as frequency is not that specific algebraically special frequency. Now, what's an algebraically special frequency? That's a big topic in GR. So algebraically special solutions are a class of solutions in GR for which the Weyl tensor obeys this equation for some null vector. Now, this has a big geometric story behind it that I'm not going to get into today. But the point being is that such special solutions can be only solved when omega equals to some special k-dependent value. And this structure on the background of 4D black holes is similar to this electromagnetic duality, but it's different in two things. First of all, it has this it's dependent on this algebraically special frequency, which and when it's equal to the algebraically special frequency, that map is not invertible. And second of all, it leaves the background intact, so it only acts on the gravitational waves. All right, so what's the boundary manifestation of this? So if we have energy momentum correlators, we put the background on a slightly curved background, and again we get this splitting into the longitudinal and transverse channel. In the longitudinal channel we get things like sound, and in the transverse channel we get things like momentum diffusion. And now this self-duality relation that I showcased before is endowed with this special structure. So it generalizes to a formula like this. So it's very similar, but now we have this algebraically special frequency that we've gotten from the bulk physics. I'm gonna list these algebraically special frequencies in the next slide. And this modifies so this, for example, will hold for energy momentum correlators in a theory dual to Einstein ADS4 bulk. And the spectral duality relation still holds, but it's now modified by multiplying it with this extra factor. This extra factor that depends on this algebraically special frequency. So the only real new input from bulk physics that we have is this algebraically special frequency. And now again we can compute the transverse spectrum from the longitudinal and vice versa. And now to illustrate what's actually going on here, and to show you what these algebraically special frequencies look like as computed from the bulk physics. So first we consider the neutral Schwarzschild case. And these algebraically special frequencies are something that's very easy to compute, and they're also very simple functions of momenta, but they're non-trivial functions of momenta. So in the neutral Schwarzschild case, it's just it's imaginary, it's proportional to k to the 4 over energy density of the equilibrium state. And for example, in the neutral Schwarzschild case, that's interesting because it tells us about the large momentum behavior of the diffusive mode. So it turns out that the diffusive mode asymptotically approaches this algebraically special frequency. Now we can consider grand canonical ensemble, so that's going to be dual to Reiser-Nordström black hole. And now these dualities that I talked about in this slide, they're actually going to mix between the electric and magnetic components of both the metric and the gauge field. They're going to mix it in some very non-trivial way, but at the end of the day, we get some equations like this, and we get the algebraic special frequencies, which are some function of momentum, charge density, and energy density. And in the boundary theory, this duality is going to mix correlators that are energy, energy charge, momentum, charge, and so on. And there are other models for which one can see that this sort of dualities exist. One is the axion model by Withers and Andrade, and there one can also show that this duality exists. So I'm not going to spend too many words on this model right now. But point being is that there are many models for which one can compute these things, and such dualities exist. Now,
can I ask something?
Yes,
Sorry,
yes.
Do you have pure gravitational models where you can have the self-dual modes? Do you know if there are any, just pure gravity?
It's,
Without
yeah,
any-
I mean, the neutral Schwarzschild is just gravity, because it doesn't couple to the Maxwell field. So you get that.
Okay. So that's a pure gravitational fluctuation, and you have this self-dual point. So you have a non-trivial Weil tensor in this case?
Yes. Yes. So to cast this into a bigger picture, so note that, for example, if we take this Reisner-Nordström case, so here we have two channels. One is sort of Maxwell channel and one is sort of the metric channel. They all mix, but if in the zero charge limit, one reduces to pure metric and one reduces to pure Maxwell. And the one that reduces to pure metric then just becomes this. It completely decouples. We just have metric fluctuations and we get the neutral case. And the Maxwell channel, so the current correlator channel, in the zero charge limit, this algebraically special frequency escapes to infinity. And what happens here is essentially that this term here goes to zero, and we recover the well-known story of the Maxwell electromagnetic duality. So this appears to be the generic. Furthermore, if we take the zero temperature limit of the Schwarzschild, which means the energy density of the boundary theory goes to zero, then this neutral omega star is going to diverge. And indeed, what we get is a sort of spin 2 analog of the electric magnetic duality, which exists on a pure ADS space for linearized perturbations. But we cannot, that's not useful for our discussion because that's zero temperature limit, so we don't get meromorphic functions out of it anymore. But what I want to say is this omega star to infinity limit essentially reduces to these well-known cases of electric magnetic self-duality, or in the boundary theory, particle-vortex self-duality. And that works for the Maxwell field or the analog for the graviton. And here I want to return to what Anastasios asked. So Anastasios and Lake had a paper in 2003 where they have discussed that, where they deform the theory with a sort of t-squared deformation, and you can sort of exploit this electromagnetic self-duality of the graviton for and get an equation just like this, the self-dual equation. And now this is a sort of a thermal generalization for this, and at finite temperature, these interesting thermal effects that are encapsulated in this algebraically special frequency seem to arise. And nobody at this point understands what this means in QFT. So we understand the bulk geometric picture of that, but why this structure and why this self-duality arises with this algebraically special structure and these momentum-dependent frequencies in the bulk is unclear at the moment. What is interesting, though, is that these are very messy computations on the gravity side, but the only imprint on the boundary theory that's important seems to be this algebraically special frequency that you can see written here for various cases. So to elaborate on these dualities with these algebraically special frequencies are unique to 4D, and that's expected because in these self-dual limits they reduce to the more familiar electromagnetic self-dualities that we know and love. We can use them to derive these spectral constraints between the spectra, and we can compute one spectrum from another. We can compute the transfers from the longitudinal, and the only real input from the bulk is what the value of this algebraically special frequency is. And interestingly, we can take this Reisner-Nordstrom case, and we get this complicated structure that mixes electric and magnetic fields and the metric and the gauge field and all of that, but it actually leaves the background intact. So if we just did a simple electric-magnetic duality in the bulk, we would change a Reisner-Nordstrom black hole into a dionic black hole with a magnetic charge. But that doesn't happen here. It really only works on perturbations. It exists, one can verify it. It's unclear why it exists, especially from the QFT side. It's unclear what the fundamental reason is. But we understand now that these dualities do reduce to the familiar electromagnetic or particle-vortex self-duality, or the spin-2 analog of the particle-vortex self-duality, which essentially Petko and Ley described 20 years ago in their paper. And yeah, this is actually not understood at all in terms of the QFT. Are there any questions about this algebraically special dualities? It's quite it's very weird in a way that these dualities exist, and it's quite confusing that they're controlled by these special frequencies that just sort of appear from the bulk. So the number of satisfying explanations that I can offer is sort of limited, but it is impressive that these dualities do manifest themselves in the boundary theory, and they allow one to completely determine the transverse channel from the longitudinal channel and so on. Okay, so to conclude, in the general picture, what I really wanted to say today is that the spectra of meromorphic correlators are heavily constrained. They're heavily constrained from the perspective of the thermal product formula, their asymptotic behavior, and it's especially relevant for the study of double trace deformed CFTs. And these constraints might hold for models with no known holographic duals. And in CFT trees, there are these self-dualities that map within the same theory. They endow this spectral duality relation with this algebraically special structure, and while we don't understand this from the QFT side, it does hint at the fact that there might exist a web of structure like that we don't yet understand. And then the structures impose rigid spectral identities within the same theory. And yeah, they depend heavily on these geometrical features of the bulk, specifically these algebraically special solutions. And I think there are several interesting things to do with that. Now, what I think is the most interesting future direction is to try and make contact with between this and what the people here in the audience, a lot of the people here in the audience are doing with their beautiful thermal bootstrap calculations. So I think that would be interesting to... I think it's clear to all of us that these things are really extremely constrained, and that we all have the urge to try to find out what one can get just from these constraints alone, and how one can translate that to more general theories. And with that in mind, of course, finding explicit models that don't have a very simple holographic dual would be desirable and very interesting. So one immediate generalization of this is, for example, if we want to study these dualities, when we turn on expectation values and sources, the thermal product formula becomes a bit more subtle, gets more structure. So there was a talk by Bhattacharya here in the thermal seminars where they did exactly that. So that's very interesting. And another interesting question is, what is the emergence of this algebraically special structure on the boundary, and reason behind these dualities at finite temperature, at finite chemical potentials, these self-dualities from the boundary theory. Because the story is not that simple anymore as it was with double trace deformations, because we have this momentum dependence, frequency dependence. So that is completely unclear at the moment, but it's a very interesting question. So that was all from me. Thanks a lot for your attention, and I welcome any and all questions.